guys. I don't seem to be able to find the other remote control for that one. So unfortunately, we're doing it in one screen today because I don't know where the IT people are. Hello. All right. Just to start with today, I'm just going to quickly go over what we covered yesterday, and then I'll give you a question to solve quickly, and give you a lecture, and then we're going to do 3 tutorial questions if you have time. Sounds good? We learned that work is a function of change in thermodynamic parameters, so pressure, temperature, and volume. So in a system, the change in your volume, temperature, in this case, the change in the distance that your piston moves is your work done. So these are the things we covered yesterday. Volume work is also related to the volume change in the system. So the piston moves, the boundary moves, and work is done. And we covered these equations. It's the integral of the change in volume. For an isobaric process, when the pressure is constant, only volume changes. Volume in an isothermal process, so when temperature is constant. This is a function of volume or pressure. So your temperature is constant, and it's the integral of your volume or pressure. So, quick summary. You have a cylinder that initially contains 0.4 cubic meters of air at 100 kilopascals and 80 degrees Celsius. The air is then isothermally compressed to 0.1 cubic meters. Determine the work done during this process. Assume ideal gas. I'll give you 5 minutes, and I'll walk around. And also look for the remote. Is it louder or not louder? Does it work? Does this work? Okay. It's not. Does this work? Yeah? Am I louder? Not louder? Okay. How about this one? No? Okay, today's not going that well. And this is not working. I'll just shout. Oh. Is this better? Okay, it's better. Guys on Skype, can you hear me now? All right, shall we continue? So, since volume work is a function of volume, and we're changing the volume, and PV equals nRT, we know that volume work is equals to minus PV times log of the changing volume. So, we're talking about minus 55.5 kilojoules. Can I get a show of hands who got that? And hands who didn't get that? So I know who tried. All right. Okay. We'll work through something similar in the tutorials anyway. So, next step is isobaric process. I think this is quite loud now. What is an isobaric process? We've covered this. Can I get one answer from anyone? Isobaric process, yeah. Loudly? Louder?
Constant pressure.
Cool. See, you can't hear me there, I can't hear you here. Let's start with changing work, right? Volume work again. So in a constant pressure is obviously not changing, so you can take that out of your integral. So the change is only volume dV. That will give you volume work in relation to change in volume. So your volume work is minus P multiplied by V2 minus V1. So your change in volume. Yeah. Using the ideal gas law, you can basically calculate all the three parameters, thermodynamic parameters from this simple analysis. So you can, because your pressure is constant, you can calculate the temperature as well. So, and just to emphasize that it's, even though it is a mathematical term, the negative, even if you don't put the negative there to begin with, and you calculate it, you just need to put the negative afterwards. But this equation will give you that convention that we were using. So in case you see it in the book, there is no negative, it doesn't mean it's the wrong equation. It's just, you need to remember compression, heat, positive, expansion, cooling, negative. So if you're heating a system, it's positive. And if you compress a system, it heats up, so it's positive as well. And when you depress the system, it cools down. So if you use a deodorant, you press the button on it, all the gas starts leaving. There's Joule Thomson effect, it actually cools down. So you can play with that later. The change in internal energy in an isobaric process is U2 minus U1. So the change equals the heat input minus the change in volume in relation to pressure. So if you rearrange that, you can calculate the heat input. But what is enthalpy here? Enthalpy is a change in energy as a result of thermodynamic process, right? So how can we apply this to the previous equation? So enthalpy is the sum of internal energy, pressure, and volume. H equals U plus PV. So the change in enthalpy equals the change in U plus the change in volume in relation to isobaric process. Therefore, your change in your heat input is equals change in enthalpy for ideal situation. So if you go through those equations, you'll get Q equals delta H. Ideal gas enthalpy is a function of temperature. And you can rearrange that to calculate Q equals change in enthalpy equals NCP delta T. So, and the assumption is Cp is independent of temperature, right? In this for ideal situations. And remember, you've all studied this in physics. Q equals Cm delta T. I think a lot of you guys remember it from, I think if you studied in Scotland higher physics, advanced higher physics, A levels, it's always that. So basically we're going through that and deriving the equation. So the work, the area under this graph is the work done. Remember there is no change in temperature, so it's constant pressure. Sorry, there is a change in volume, not pressure. Isochoric process. What does isochoric mean? Can I get one loud answer? Anyone? We've covered constant pressure, we've covered constant temperature. What's left? Thank you. Volume is constant. So there's no boundary work. We've done the question yesterday in this. It's a rigid container. So when there is no movement, it could be any rigid container, it could be a system with a piston where you lock the piston in place, or the pressure out, on the opposite side of the piston equals the pressure on the other side. So you have a gas at 200 bars on one side of the piston, another gas at 200 bar on the other side. So you have a rigid system, even though there is a piston. So volume work in this case equals the change in the system in relation to PdV. So since dV equals 0, there is no volume work, as we discovered yesterday from that question. So for an ideal gas system, Q equals change in internal energy, which equals NC delta T. The difference between CV and CP, what is the difference, do you think? I mean, it's labeled. I think. All right. CP is obviously related to pressure. CV is related to volume in relation to the universal gas constant, and we'll get to the end of that by the end of this lecture. So your CV is the relationship between the internal energy, the change in internal energy over the change in temperature, the partial derivative, and your CP is the partial derivative of the change in internal energy over change in temperature plus the change in the relationship between change in volume and change in temperature. Yeah. This is the relationship you need to know to understand, but you won't be solving this until next year and the following year. So what's heat capacity? The heat capacity is basically the capacity for the storage of heat within a system, and you can calculate that, and that's determined by the molecular movements in your system. So it's a function of heat transfer, the path function. So for a general path function, your change in internal energy, molar change, over change in temperature, it gives you your heat capacity. But the heat capacity for volume work and pressure work are different. and we're going to go through what's the difference. And remember the first law of thermodynamics: the change in internal energy equals the heat plus the work into the system. So the differential form of this would be the change in heat equals the change in internal energy plus the change in volume in relationship to pressure. Since we are considering an isochoric system, the change in volume is 0. Hence, for an isochoric system, the change in heat equals the change in internal energy only. Because the volume doesn't change, there is no work done. So work is 0. So isochoric, all energy is stored internally. Hence, Cv equals the relationship between du over dt. For an isobaric system, so we will start with the molar enthalpy. You know the enthalpy equals the internal energy plus PV. Right? So there is no pressure change. Hence, the change in enthalpy equals du plus dPV. And in that continues to be dH equals du, internal energy, plus PdV, which is the change in volume plus VdP, because you have your change in volume and you have your change in pressure. Since dP equals 0, then for an isochoric system, the change in enthalpy equals change in internal energy plus PdV. And again, remember the first law of thermodynamics. So the change in internal energy equals dQ minus PdV. Therefore, in this case, dQ equals dH. Following that? Yes? Maybe up. So since the general heat capacity path is the C path dQ over dt, then Cp equals dH over dt. It's a relationship between the enthalpy and temperature for Cp. How many remember that from last semester, I assume? Can I get a show of hands of people who remember this? Okay, and the rest I assume don't remember, right? Okay, I'll put a video up on this that explains the kinetic theory of gases and also everything else I've covered. I found a really good video. I'll put that on Vision today. So, your PV equals 2 over 3, the number of particles multiplied by m average velocity squared over 2. Your mv squared over 2 is basically the kinetic energy of your particles, and n is the number, so you can calculate the exact kinetic energy of your particles. Hence, you can calculate the volume and the pressure. So because pressure and volume are a result of the particles moving around, jumping around, hitting the side of your container. And and also PV equals nRT, which equals n over NART. NA is your Avogadro's constant, so it's effectively the number of moles. So you can calculate the velocity of the particles for that number of moles. And hence you have 3 over 2 RT equals the number of Avogadro's constant multiplied by mv squared over 2, which is your kinetic energy for that mole of substance. It only applies to monoatomic gases, and we'll go over diatomic gases as well. So for monoatomic gases, the store of energy is transitional kinetics. So it's all about the movement of that monoatomic particles. It comes down to the rotation, how they rotate. And I'll get back to that in a second. So the internal energy for that monoatomic gas is the Avogadro's constant multiplied by the kinetic energy. and hence the internal energy equals 3 over 2 RT. It's from the previous equation. Yep. So this shows for an ideal gas, the internal energy is directly related to temperature only. And remember, Cv equals du over dt. So differentiating with respect to t gives you Cv equals 3 over 2R. Yep, U equals 3 over 2R T. Remember that, we'll come back to that. So it only applies to monoatomic ideal gases. Remember that, it's important. For diatomic ideal gases, equal partition theorem applies. So for low temperatures, there are two modes of rotation. So imagine you have two particles, and there's only two ways they can rotate. They can either rotate clockwise, anti-clockwise, right? In one plane. So you have X, Y, Z plane as well. It comes from quantum mechanics, but just remember you have 2 times 1 over 2R. And at higher temperatures, you also have vibration. So you have the rotation, also these molecules, because they're moving around, they're hitting each other, so they vibrate. They're hard spheres. So for diatomic gases at low temperatures, Cv equals 5 over 2R. So that, you have your 2 times 1 over 2R. And hence, what happened there? Okay. Hence, your enthalpy is U plus PV. And using your ideal gas equation state, you have H equals U plus RT. And hence, your internal energy is related to temperature. And your enthalpy is also related to temperature. So dH over dt equals du over dt plus R dt over dt. And Cp equals Cv plus R. So you can calculate the universal constant if you have Cp and Cv. So that's one of the ways. That's basically how they originally calculated it. But then if you measure Cp, you can calculate Cv because you have the universal gas constant, and you can use that in various different for refrigeration, whatever you're using, because you need the heat capacity. Since for monoatomic gas, Cv equals 3 over 2R, and remember Cp equals Cv plus R, then you can calculate Cp for monoatomic gas as 5 over 2R, just substituting into that equation. And for diatomic gases at low temperature, Cp equals 7 over 2R, so you have rotation, again for diatomic. And for polyatomic gases, so diatomic and above, the heat capacity is temperature dependent. So for an ideal gas, the heat capacity is only a function of temperature. Remember, it's an ideal gas. So Cp equals Cv plus R. And that's pretty much time for a question, I think. Any questions before I move on? Too quick? Way too quick? Okay. All right. I think, would you prefer me to work through it on that next time? On the board? Yes? No? Maybe? Can I get a hands? No? Just slower? More explanation? More explanation? Can I get hands too quick? Okay. Way too quick. All right. Fair enough. All right. I think we'll go through the questions. I'll work through the questions with you because it pretty much explains everything I've covered. Happy about that? Yes? No? Okay.